In this video, we are going to introduce Faraday's law of electromagnetic induction. In general, there are two laws of electromagnetic induction: Faraday's law of electromagnetic induction and Lenz's law. Faraday's law concerns with the magnitude of the EMF induced, and Lenz's law concerns with the polarity of the EMF induced. We will focus on Faraday's law in this video, and in particular, use the coil system to introduce how it works. So, what is Faraday's law of electromagnetic induction? We have seen earlier in the videos that the EMF induced in a coil or a conductor depends on factors such as magnetic flux density, area of the coil, the number of turns of coil, and the angle that the magnetic field makes with the coil. That is, the EMF induced depends on the flux linkage of the coil. Furthermore, we see that only when there is a change in the flux linkage, there will be an EMF induced. The faster the change, the larger the EMF induced. The last experiment also shows that when wires are made to cut the magnetic flux lines, there is also an EMF induced as well. Faraday's law sums the results out and states that the magnitude of the EMF induced is directly proportional to the rate of change of flux linkage or to the rate of cutting of magnetic flux. When written in equation form, it gives E proportional to d phi dt, where d phi represents the change in flux linkage or amount of flux cut. Although there are two forms of statement, they are often equivalent, which I will illustrate shortly. Before we start with the illustration, just note that you may have come across another form of Faraday's law in books, E equals to minus d phi dt. This, strictly speaking, is not really Faraday's law, but rather is the result after combining with Lenz's law, which is able to explain the negative sign of this equation. However, most people will refer to this final equation as Faraday's law. As this is a more practical form of the equation, we will also use this form subsequently. To understand Faraday's law, let us use it to explain a simple case where we have a coil of wire that is moved closer to a magnet from position X to position Y. As observed in the earlier video demonstrations, we will observe an EMF induced in the coil as the coil is moved from X to Y. There are two ways to explain Y using Faraday's law of electromagnetic induction. Firstly, using rate of change of flux linkage, and secondly, using rate of flux cut. Let us look at the first method of explaining why EMF is induced using rate of change of flux linkage. When the coil moves from X to Y, we see that in the picture, the number of flux lines through the coil rises from 3 to 5. We also see that for the same area, since the number of flux lines increases, the magnetic flux density increases. Hence, we can deduce that the flux linkage of the coil increases, and by Faraday's law, which states that the EMF induced is proportional to the rate of change of flux linkage, therefore, an EMF will be set up in the coil. Let us now try to explain the phenomenon using flux cut. We see that in moving the coil from X to Y, it will actually cut through two flux lines. Hence, by Faraday's law, an EMF is induced in the coil as the coil cuts the flux lines as it moves from X to Y. What is interesting to note here is, earlier we had 3 flux lines changing to 5 flux lines. 5 minus 3 is 2, so the flux linkage changes by 2. In this case, we also have 2 flux lines cut. So we see from the two cases, the change in flux linkage is similar to the flux cut explanation. So, are there any other ways where we can induce EMF in a coil system? Recall that the flux linkage of a coil is given by N times B perpendicular times A, which is equals to NBA cosine theta. Since Faraday's law of electromagnetic induction gives E equals to minus d phi dt, therefore we see that we can induce an EMF in the coil by changing any one of these variables here. The easiest way, of course, is to change the magnetic flux density with respect to time. From E equals to minus d phi dt, we see that changing the magnetic flux density is the same as changing the whole flux linkage. Hence, we can increase the flux density, and that will induce an EMF that will cause the induced current to flow. So this is increasing the flux density. Alternatively, we see that we can also decrease the flux density, and that will also change the flux linkage in the coil, and that will also induce an EMF that will cause the induced current to flow. If there is no change in the flux density, there is no change in the flux linkage, and no EMF is induced, and there is no current in the loop. The next thing we can do is also change the area of the coil with respect to time. Again, given that E equals to minus d phi dt, changing the area will change the flux linkage with respect to time. So if we have a coil that's made with some stretchable wire, if we allow it to stretch, it will cause an EMF to be induced across the coil. Lastly, we also see from the flux linkage equation that we can change the angle theta with respect to time. This can be done by rotating the coil in the magnetic field. This is the basis of our electric generator, which we will cover a little more in detail later. In summary, for this video lesson, we have introduced the Faraday's law of electromagnetic induction, where it states that the magnitude of the EMF induced is proportional to the rate of change of flux linkage or to the rate of cutting of magnetic flux. We have also seen that to induce EMF in a coil of wires, we can either change one of these variables. Usually, B, A, or theta are changed to cause a change in the flux linkage.